Hello everyone, in today's video we're going to solve another dynamics problem involving a chain, and the setup this time is that we have a smooth inclined plane. Maybe it's a table that someone has lifted up at one end, and there's a chain which is fully stretched out along the table with part of the chain hanging vertically off the edge of the table. Now, a few of the key parameters of this problem are that the angle that the plane makes to the horizontal is theta, the total length of the chain is L, and I've defined x of t on my diagram just to be the length of chain which is hanging vertically. So that's going to, of course, start increasing as soon as we allow the chain to slide. But I've said also that the initial condition is that x initially takes the value x0, where x0 is just some constant. And so initially someone is holding the chain, maybe up at its top end, then at some time, which by definition is t equals 0, we let go of the chain and just let it start sliding down from rest, so that v of 0, the velocity, downwards velocity, is also initially 0. So there are three things I'd like to find here. Firstly, x of t, so how the amount of chain hanging down varies with time. Also v of t, so how the velocity of the chain varies with time. And finally, v as a function of x, so the velocity as a function of how much chain is hanging down. Simply because depending on what kind of question you're trying to answer, v of x can sometimes be more useful than v of t. For example, there is a classic physics problem, usually just with a horizontal surface, but it says something like, what's the velocity of the chain at the instant when the last link leaves the table? In that case, v of x would be more useful than v of t. Now, what's going to allow us to solve this really is the fact that the chain starts under tension. In other words, it's fully extended and it's always being pulled down, so it's going to remain always under tension. And so the total length of the chain is not going to change. So we're going to approach this by considering forces and using Newton's second law to figure out a differential equation for x as a function of time. Now, there are really just two forces acting on the chain, its own weight and the normal contact force between the table and the chain. So let's draw some arrows on just to show those forces. I'm going to split the weight into two different parts though, the weight of the vertical bit and the weight of the sort of diagonally sloped bit. So I'm just going to put a little arrow down here. That's the weight of the vertically hanging bit. It's going to be, well, the mass times g. What's the mass? Well, to specify the mass, I'm going to introduce a new parameter, which I'm going to call lambda, which is the mass per unit length. Right? I didn't specify that initially when I stated the problem, because as it turns out, interestingly, lambda is not going to enter our final result, but it's a useful parameter to define here. So lambda is the mass per unit length. Multiply that by the length x to get the mass of the bit that's hanging down, and then multiply by g to get its weight. Now, the weight of the part of the chain which is sitting on the table is going to be acting at its center of mass. So I'll draw a downwards arrow going sort of in the middle of that sloped bit. This is going to be, again, lambda, mass per unit length. The length of the sloped bit is going to be L minus x, because the total length is L, and then we just multiply by g to turn it into a weight. It's also useful, because we're going to be resolving forces just now, it's also useful if I draw a dashed line that's perpendicular to the plane. I just note that this angle in here between the weight and that perpendicular is also theta, which follows from basic geometry. You can prove that just using the fact that angles in a triangle add up to 180 degrees, in fact. And for completeness, I guess I'll add in the normal contact force. It's really distributed along the entire length of the chain, but I'm just going to draw it acting at the center of mass. Let's say it has a magnitude of n. Now, if you think about it, only the components of the forces which act along the direction of the chain are actually going to cause any acceleration of the chain. So we're going to essentially resolve our forces in the direction of the chain, which probably sounds a little bit strange because the chain has two directions, right? Part of it's vertical and part of it is at an angle, but that's okay. So if you want to write down the resultant force in the direction of the chain, well, firstly, you've got lambda xg, this weight here, which is all acting along the direction of the chain, so we don't have to do any resolving or anything. This other weight here, however, we do have to project along the direction of the chain, and that's going to involve multiplying it by sine theta. So I'm going to get a lambda plus lambda L minus x g sine theta. The normal contact force is perpendicular to the direction of the chain, so that doesn't enter our equation of motion. And so this is your resultant force. We're just going to set this equal to mass times acceleration. Now, because the chain is always under tension and it's always fully extended, we don't have to worry about different parts of the chain accelerating at different rates or anything. The entire chain accelerates at the same rate. And so for my mass, I can just put lambda L as the mass of the whole chain, and I can just put x double dot because, well, clearly the element at the very bottom is accelerating with an acceleration of x double dot, but we just argued that the entire chain has to be accelerating at the same rate. If you're not entirely comfortable with the idea of adding together components of forces, like this one and this one, which are technically in two different directions, then there is another way you could think of this. You could think of each section of the chain separately, so the vertical bit and the sloped bit, and then you'd say, well, there's a vertical tension pulling up on the bottom bit of the chain, and then a tension pulling along the direction of the slope on the slope part of the chain. Then you treat the two bits separately, set up an equation of motion for each part of the chain, and you can then add your two equations together. T will cancel out, and you end up with something equivalent to what we got originally. So now what we have to do is solve this second order differential equation for x as a function of time. Let's do some algebra and then some calculus. First thing I'm going to point out is that the lambdas cancel because they're present in each term. That's already interesting. It means the mass per unit length, or equivalently the total mass of the chain, won't enter into our final result, and I'll say a bit more about that from a physical perspective later on. I'll also point out that x appears in two different places. We don't really want that, so let's regroup the terms a bit. So we divide everything by lambda and then expand the brackets, and we're going to refactorize so that we take out a factor of x, or more specifically gx. So you're going to have, let's put it up here, gx, you've got 1, and then you've got minus sine theta from that original bracketed term, and then left over you have just plus gl sine theta, which is a constant, and that's equal to now lx double dot. We can put this into a slightly more familiar looking form by dividing everything by L and moving some of the terms around a little bit. So we're going to get x double dot. We put the x term on the same side as the x double dot, and you get g over L into 1 minus sine theta, which is the coefficient of x. That's now equal to g sine theta, and the reason I think this is a good form to put it in is this now looks very much like a simple harmonic motion equation with a couple of differences. Firstly, this is a minus sign instead of a plus sign, and secondly, the right hand side is not 0, so you can interpret the right hand side as like a constant forcing term. Now, just so that we've got a bit less writing to do, I'm going to define a couple of derived parameters. Write this as x double dot minus p squared x is equal to q, where I've just defined p squared as the coefficient of x, right? So g over L 1 minus sine theta, and the q is just the right hand side, so that's g sine theta. The reason it's okay to say that this is p squared, by the way, is that sine theta can never be bigger than 1. Therefore, 1 minus sine theta is always a positive quantity, and so we may as well define this as p squared because that automatically makes it positive. It also makes the algebra work out a little bit more neatly. Now, the full solution of this differential equation will be the sum of two parts, the complementary function and the particular integral, where the complementary function comes from pretending that the right hand side is 0 and solving that, and the particular integral is an extra bit that you add on to make the right hand side work out correctly. I'm not going to introduce those methods from the beginning. I'm assuming you're vaguely familiar with all of that stuff. The complementary function I'm going to denote as x subscript cf, and I'm pretty much going to quote the solution here. It is a times hyperbolic cos of pt plus b times hyperbolic sine of pt, where a and b are arbitrary constants to be determined by the initial conditions. If you want to, you can substitute that back into the left-hand side of the differential equation and show that you get 0. So it's verification that it works. If you want to derive that from scratch, the usual way to do it would be to substitute a trial solution. X is proportional to e to the something times t. Figure out what that something, the missing parameter, has to be, and you find that your solution is a superposition of positive and negative exponentials, but then we can switch basis to hyperbolic functions because they're derived from positive and negative exponentials. Another thing to point out is that this looks very similar to the solution for the simple harmonic oscillator, except because you have a minus sign instead of a plus sign there, you get hyperbolic functions instead of ordinary trig functions. So what about the particular integral, which I'm going to call x subscript pi? Well, because the right-hand side is just q, and q is a constant for any given setup of this problem, we just guess a constant. We just guess that x is some constant, and I'm going to call it capital C. We substitute that in, and we figure out what c needs to be to make everything work out. So if you differentiate c twice with respect to t, well, you just get 0 because c is a constant. And then the minus p squared x is just going to be minus p squared c, and that is supposed to be equal to q. And then straightforwardly, we get that our constant c has to just be minus q over p squared. That means your full solution for x is just a superposition of those two parts. So I'm just going to copy the complementary function. So it starts with that, and then we just add on the particular integral, which is minus p squared. So there's the general solution. Now we want to apply our initial conditions and determine the unknown parameters a and b. In order to do that, we're going to have to differentiate x because one of our initial conditions was v of naught is naught, and v is the derivative of x. And so differentiate that, you just get pa and then hyperbolic sine of pt. And then similarly, your second term is just pb. Now it swaps to hyperbolic cos of pt, and the final term disappears. So we've got x and x dot in terms of the unknown parameters a and b. Let's apply our initial conditions, calling it IC. The first one was that x at time 0 was just x0, so we use our expression for x. The left-hand side is just going to be the constant x naught. Then we get a cosh of naught, which is just a times 1, which is a. Sine of naught is naught, and so that term disappears, and you just get a minus q over p squared. And then straightforwardly, that rearranges to give you a in terms of the other parameters. So a is x naught plus q over p squared. The other initial condition was that v or x naught at time naught is also 0. And so from your x dot equation, 0 on the left-hand side, the sine term disappears, and you get, well, just pb cosh naught, which is pb times 1. And that gives you that b is equal to 0. We are assuming there, by the way, that p is not 0. I'll say a bit more about that from a physical perspective later on in the video. For now, just notice that if p was 0, we would actually have a totally different differential equation. Just x double dot is a constant, and this solution wouldn't even apply. So if we're going for our hyperbolic cos and sine solution, then it's safe to assume that p is non-zero. So just to summarize, here is our solution for x as a function of time. I haven't bothered writing in the hyperbolic sine bit because we found that its coefficient b was 0, and we've got a bunch of derived parameters p squared and q and a, which are defined in terms of the original parameters of the problem. One thing to notice is that the combination q over p squared is important because it appears in x, and it also appears again via a. So we should probably focus on that specific combination and work out how to write q over p squared in terms of the parameters of the problem. Q is just g sine theta, and p squared is g over l into 1 minus sine theta. Then we remove the nested fractions and cancel the g's, and we find that it's just equal to L sine theta over 1 minus sine theta. So just for completeness, I've written out x and v as explicit functions of time in terms of all of those original parameters, just so that we can see all the various dependencies. So let's take a few moments to just consider some special cases and develop some intuition for the meanings of these equations. Firstly, two interesting limiting cases of theta to consider are 0 and 90 degrees, or pi over 2. I don't have much to say about the theta equals 0 case, other than if you plug in theta equals 0, a lot of the terms disappear, and you get a greatly simplified expression. That corresponds, of course, to a horizontal table, which is kind of the standard version of this problem that you might see around. The opposite end of the limit, in other words, theta is 90 degrees, corresponds to the table or the plane being vertical, which, if you think about it, is actually totally equivalent to just taking a chain and dropping it vertically because it's not in contact with the table if the table is vertical. So if you take theta and take it towards pi over 2, then sine theta goes towards 1, and you can already see that this whole solution kind of breaks down because you've got 1 minus sine theta in various denominators. And so what's going on there is kind of related to what I was saying earlier, which is that p cannot be 0 if we're going with these solutions right now. If you look back at the definition of p squared, you can see that p is only 0, if sine theta equals 1. And so the conclusion of all this is that as the table becomes vertical, p becomes 0, and our differential equation doesn't work anymore. In fact, when p becomes 0, in other words, sine theta becomes 1, or theta becomes 90 degrees, your differential equation just reduces to x double dot is equal to g. In other words, the entire chain is in free fall, which makes a lot of sense if it's just vertical and not in contact with the table. So those two limiting cases of theta do make physical sense. Other things we can check here are how x and v change their behavior if we vary the parameters g and l. So because g only affects the time dependence via the argument of the hyperbolic cos and the hyperbolic sine, we can see that if you take this g here and you just make it bigger, then the coefficient of t is getting bigger. That means your hyperbolic cos is going to grow more quickly with time, and similarly the hyperbolic sine will grow more quickly with time. In other words, if you make the gravitational field strength bigger, x and v both grow more quickly. That makes sense because bigger g means you're pulling down the chain more strongly, essentially. Of course, increasing L has the opposite effect because L appears in the denominators of those coefficients of t. So if you make L bigger, you make x and v grow more slowly with time. Now, that makes physical sense because if you increase the length, you're adding more inertia to the chain, and so everything is just going to happen over a slower timescale. And on the subject of inertia, the other thing I want to comment on with these solutions, as I mentioned earlier, is that neither of them depend on the mass of the chain or the mass per unit length of the chain. I think this ultimately comes down to the same reason why the period of a pendulum doesn't depend on the mass of the pendulum. It's because of the equivalence of inertial and gravitational mass, right? If you increase the mass of the chain, you increase its inertia, you make it harder to accelerate, but by the same proportion, you also increase the gravitational force, you increase its weight, and those two effects perfectly balance each other out. Now, the other thing that we wanted to find was v as a function of x. There are two approaches to doing this. The first is to note that we already have x as a function of t and v as a function of t, and so we can combine those and eliminate the time variable using hyperbolic trigonometric identity. Now, I'm not going to take that approach for two reasons. Firstly, the algebra doesn't look that appealing given all the various parameters involved. And secondly, I think there is a more physically interesting way to go about finding this. So the method that I have in mind is the conservation of energy. Now, when you're dealing with problems with chains, you have to be very careful because it's sometimes easy to think that energy is conserved when it actually isn't. I will be going through a problem in my next video where that's the case, so I'll say more on that next time. But in this case, there are no dissipative forces, there's no friction or drag, there are no inelastic collisions or anything, and so we can safely say that energy is being conserved in this case. So let's start by writing down an expression for the total initial energy of the chain. So I'm going to call that E subscript I, initial energy. And we need to define a zero level for our gravitational potential energy. I'm going to define it to be basically this dashed line, a horizontal line that goes through the lower left corner of the table or the plane. So you've got essentially just two different contributions to the gravitational potential energy. You have the bit of the chain that's hanging down. We pretend it's all at its center of mass, which is at a distance x over 2, or x naught over 2, because we're considering the initial energy. So the gravitational potential energy is just mgh, and the m there, the mass, is mass per unit length lambda multiplied by the length x naught. Then we just put our g there, and we said the height was x naught over 2, but it's actually minus x naught over 2 because the center of mass is below our reference point. So we've got negative gravitational potential energy. Then by a very similar logic, we add on the gravitational potential energy of the part of the chain which is on the slope. So I'm going to put plus this time because its center of mass is above our reference point. We've got our mass, which is lambda times the length which is on the table, which is simply going to be L minus x naught because the total length is L. Then we put our g. You do have to project the distance of the center of mass above the reference point onto the vertical axis, but that's fairly straightforward. We just multiply by sine theta, right? So you get L minus x naught sine theta, and again we divide by 2 because the center of mass is halfway up that part of the chain. So we can tidy this up a little bit by noticing that there's a common factor of a half in both terms, and there's also a common factor of lambda g. So I'm going to take that out. I'm going to put the second term first because it's positive, and that's going to be L minus x naught squared times sine theta, and then we just take care of the first term by subtracting x naught squared. So now we can equate this to the energy at some arbitrary time, because we said that the energy was conserved. Now the energy at an arbitrary time is going to look very similar to this, except the x naught will be replaced by x, and there'll be a kinetic contribution as well, because the chain is only stationary at time t equals 0. So I'm going to start by copying out this entire expression and changing my x naughts to x's, because we want to make this more general to get the gravitational potential energy at some arbitrary time. I'm going to add on a kinetic energy contribution. Now the whole chain is moving with the same speed because it's inextensible, and so we just get a half mv squared. The mass is lambda L, where L is the total length, times that by v squared, and we just add that on, and that's our general energy at some arbitrary time. All we have to do then is go back to our original expression and equate those two things. Now a couple of things cancel. You've got factors of a half everywhere, and you've got factors of lambda everywhere, which is consistent with what we did with forces, and we found that results don't depend on lambda. So if we just divide everything by L and collect the terms together, you've got v squared is going to be g over L, and essentially I can just start by copying this stuff. It's on the right hand side of the equation. Then I'm going to copy this stuff here, but we have to flip the signs for that one because we are moving those terms over to the other side. So this is going to get a minus sign. This is going to get a plus sign. And so I've just added here what I think is the nicest final form to give our answer in. We just regroup the terms a little bit. We can consider some limiting cases as usual. Firstly, if theta is 0, then sine theta is 0. That corresponds to a horizontal flat table. Then all of this stuff disappears and you are left with a very simple solution, which you can compare against other versions of this problem that you'll find around. The other limiting case that we considered before was what happens when theta goes to pi over 2 and 90 degrees, then sine theta becomes 1. Now I'm not going to go through the algebra, all of the steps here, because it's not that interesting, but I will tell you that if theta goes to pi over 2, then v squared ends up just being equal to 2g into x minus x naught, because a lot of the terms end up cancelling. Now, if you think carefully, you'll notice that this could have been derived from the Suvat equation, v squared equals u squared plus 2as, when you've got constant acceleration. In the case where a is equal to g, again, that makes a lot of sense, because when theta is pi over 2, your entire chain is vertical, not in contact with the table, so it's just undergoing freefall. So it's reassuring that we recover our constant acceleration equation in this case. So we've solved our original problem. In my next video, I'll be going through another chain problem and stepping up the difficulty once again, and illustrate why you have to think very carefully about whether energy is conserved when you've got chains involved. So thanks for watching, and hope you'll join me for that next video.